What if I told you that one of the most simple-looking gaming consoles on the planet is hiding some of the most advanced engineering we've ever seen in consumer tech? The new Switch 2 doesn't look like a spaceship. It doesn't unfold into a robot, and it's not made of unicorn dust. Yet somehow, Nintendo is asking you to cough up a cool $450 for it, a full 50% more than the original. So, what's going on here? Did they lose their minds? Or did they secretly reinvent how handheld consoles are built from the ground up? Let's step inside the world's most advanced gaming hardware factory and find out. At first glance, the Switch 2 looks almost unchanged. Same iconic shape, same detachable controllers, same overall vibe. It's like seeing your childhood best friend after a glow-up. Familiar, but sharper in all the right places. But under that familiar plastic shell, everything has changed. And the story of why it costs so much more starts with the brain of the machine, its processor. Inside the Switch, 2 lives a chip that would make even high-end laptops jealous. Built by NVIDIA using cutting-edge 4-nanometer technology, it's so densely packed with transistors that it's almost comical. The old Switch's processor was built on a 12-nanometer process with about 2 billion transistors. The new one? Over 15 billion. Imagine cramming the population of Earth twice into a space smaller than your fingernail. That's what we're talking about here. But building something that advanced isn't cheap. Creating a 4-nanometer chip involves extreme ultraviolet light, billion-dollar manufacturing equipment, and clean rooms so sterile they make hospital operating theaters look filthy. Each transistor is smaller than a virus, and they have to be etched into silicon with atomic-level precision. It's mind-boggling science, and it shows on the bill. That tiny brain used to cost Nintendo about $25 to make. Now it's closer to $85 per unit, and that's just one part of the console. Now let's talk about the screen. Most people expected Nintendo to go all in on OLED, since that's the direction tech usually goes. But Nintendo, being Nintendo, zigged where everyone else zagged. They went back to LCD, but not the same LCD from 2017. This is a next-generation panel with full 1080p resolution on a bigger 7.9-inch display, meaning over twice the pixel density of the original. It's also rocking HDR10 support, which makes colors pop and highlights explode off the screen in a way the OLED model never could. How? It's thanks to a quantum dot enhancement layer that lets the display render over 1 billion colors instead of the usual 16 million. But here's where the engineering brilliance really shows. This screen is not only more advanced, it's actually cheaper to produce. At about $35 a unit, it's significantly less than an OLED panel, while still delivering better performance where it matters. And because Nintendo opted for this tech, they could pack in features like 120 Hz refresh rate and variable refresh rate, both of which make gameplay feel smoother and more responsive without sending cost into the stratosphere. It's a classic Nintendo move. Don't chase the shiniest spec sheet, which yet build the smartest one. Then there's the Joy-Con situation. On the surface, they look unchanged, but anyone who's owned a Switch knows the original controllers had one frustrating flaw. Over time, they'd get wobbly, loose, and start feeling like cheap knockoffs. Nintendo was determined to fix that, and their solution is pretty genius. Instead of the old sliding rail system, the Switch 2 uses precision-engineered neodymium magnets to snap the Joy-Cons into place. These aren't fridge magnets, they're rare earth components that have to be aligned within 1/10 of a millimeter. Too weak, and the controllers fall off. Too strong, and you can't remove them. It's a delicate balance, and every pair is tested for up to 1 million attach-detach cycles. Of course, that level of precision comes at a price. The old attachment mechanism cost around $12 to make. This new magnetic system? Roughly $35. But it solves a problem that's haunted the Switch since day one and dramatically improves the feel of the device. The difference might be invisible, but the moment you snap the new controllers on, you feel it. All of this extra power brings a new problem though: heat. The new processor is about twice as powerful as the old one. but it also generates roughly 4 times the heat. And heat is the enemy of handheld consoles. Too much of it, and performance tanks, components degrade, and the system becomes a pocket-sized furnace. So Nintendo had to get creative. Their solution was to borrow technology usually reserved for gaming laptops and high-end graphics cards, a vapor chamber cooling system with copper heat pipes. Inside, a tiny amount of liquid evaporates from the chip's heat, travels through the pipes, and then condenses back into liquid, a continuous cycle that wicks heat away far more efficiently than a basic heat sink ever could. Even the thermal paste that connects the chip to the cooler has to be applied by robotic arms with surgical precision. And every single heat pipe is pressure tested before assembly. It's overkill, but it's necessary, and it's not cheap. The cooling solution alone now costs about $25 per console, compared to just $8 on the original Switch, and then we get to the assembly process, the part most people never think about. Back in 2017, each Switch had to pass 23 quality control checks before leaving the factory. That number has more than doubled. Today, every single Switch 2 goes through 47 different checkpoints, each designed to catch microscopic flaws before they ever reach a customer. Robots handle the delicate steps like placing chips and applying thermal paste, while human technicians inspect for cosmetic defects and subtle assembly issues that machines can't detect. If a unit fails even one of those 47 checks, it's scrapped on the spot. Roughly 8% of all consoles never make it past the factory gates. This perfectionist approach adds about $40 to the manufacturing cost, but Nintendo knows it's worth it. A dead console on store shelves is a PR disaster. A flawless one becomes a household staple for a decade. They'd rather eat the loss on a failed unit than deal with the cost and reputation hit of mass returns later. And that's a big part of why Nintendo products, despite being handled by kids and tossed into backpacks for years, just keep working. Now let's talk numbers, because that $450 price tag doesn't come out of thin air. The original Switch cost Nintendo about $100 to $80 in parts. Today, the Switch 2 costs roughly $265 in materials alone. That's an $85 jump just in raw components. Factor in the more expensive chip, the new display, the upgraded Joy-Cons, the high-end cooling system, and the obsessive quality control, and the total manufacturing cost lands around $310 per unit. That leaves Nintendo with a profit of about $140 per console, slightly higher than before, but not outrageously so. Most of their profits still come from the games, where they make $15 to $20 on every title sold. But the price isn't just about hardware, it's about philosophy. Nintendo doesn't design products the way most tech companies do. They don't chase raw specs, they don't brag about teraflops, and they don't race to be the most powerful. Instead, they obsess over balance. Every engineering decision on the Switch 2, from the chip to the display to the magnets in the Joy-Cons, follows the same guiding principle. Give players the best experience possible without compromising portability, battery life, or fun, and that philosophy shapes everything about how this console is built. Take that 4nm chip again. Sure, it's powerful, but Nintendo didn't design it to run the latest AAA PC ports on ultra settings. They built it to deliver incredible performance efficiently. That's why, despite packing over 7 times more transistors, it sips power compared to traditional gaming hardware. It's not about brute force, it's about smart power. That's the kind of engineering that lets you play expansive open-world games on the go without your battery dying before the cutscene ends. And that's where a lot of the price increase really comes from. Invisible improvements, stuff you don't see in spec sheets or marketing slides, things like energy-efficient silicon, advanced power management circuits, and tightly tuned firmware. All of that costs money to develop, years of R&D, testing, and iteration. But the payoff is a console that's more capable without sacrificing the pick-up-and-play magic that made the original Switch so beloved. Then there's the display choice. Going back to LCD instead of sticking with OLED might seem like a step backward, but it's actually a masterclass in cost-benefit engineering. OLED looks amazing, no question, but it's expensive, harder to manufacture at scale, and not great for features like high refresh rates or HDR10 brightness. Nintendo's decision to invest in an advanced LCD with Quantum Dot Tech means they can deliver richer color, higher frame rates, and better dynamic range, all while keeping power consumption lower and cost manageable. It's the kind of nuanced decision that seems simple until you understand just how much thought went into it. And the Joy-Cons? That's another perfect example of Nintendo's design priorities. Most companies would have shrugged off the looseness issue as good enough. After all, the original sold over 130 million units despite it. But Nintendo decided to tackle it head-on. Replacing a $12 sliding rail with a $35 magnetic system is a massive cost jump for something that, on paper, doesn't make the console run any faster. But in reality, it makes the whole experience feel premium. Every time you snap those controllers on, there's a satisfying click. They don't wiggle, they don't drift apart, they just feel right. And that kind of invisible quality, stuff you can't put a number on, is what builds brand loyalty. Cooling is another area where Nintendo could have easily cut corners. They could have slapped in a slightly bigger heatsink, called it a day, and accepted some throttling under heavy load. But instead, they engineered a full vapor chamber cooling system, something you usually see in $2,000 gaming laptops, and shrunk it down to fit in a portable console. It's over-engineering at its finest, and it's why the Switch 2 can run more powerful games without turning into a space heater. So now the question's on you. Does Nintendo's obsessive approach to engineering justify the premium price? Would you pay more for something built to last and perform this well? Drop your thoughts below. Sony just dropped a $700 PlayStation. $700 for a console? And the wild part? If you put it next to the regular PS5, they look exactly the same. No shiny Pro badge, no glowing neon strips, no sleek redesign to make it feel futuristic, just two big black and white boxes that could pass as twins. One costs $500, the other costs $700, and unless you're some kind of silicon psychic, you'd never know which is which. Now that makes you wonder, why would anyone pay $200 more for something that looks identical? Well, because all the magic is happening under the hood. Sony didn't bother with flashy cosmetics. They poured every dollar into what you can't see. It's like buying a car that looks like a Toyota Corolla on the outside, but under the hood it's secretly packing a Formula One engine. That's the PS5 Pro. On the outside, same spaceship-looking console. On the inside, it's a whole different beast. And the heart of that beast? The GPU. That's the chip that controls everything you actually see on screen. The graphics, the lighting, the shadows, the reflections, the part that makes your jaw drop when you walk through a neon-lit street in Cyberpunk or swing past skyscrapers in Spider-Man. Sony didn't just give this thing a mild upgrade. No, they went full mad scientist. They stitched together pieces from 3 different AMD GPU families, RDNA 2, RDNA 3, and even some unreleased future tech. It's like they raided AMD's lab in the middle of the night and said, "We'll take a little of this, a little of that, oh, and whatever experimental thing you're not supposed to release until 2026. Mark Cerny, PlayStation's hardware wizard, calls it RDNA 2.x, which honestly sounds like a placeholder name, like they couldn't decide if it was RDNA 2.5 or 3. But here's the bottom line. This hybrid design is a monster. The original PS5 shipped with 36 compute units. The Pro, 60. That's a 67% jump. Imagine if your boss gave you 67% more coworkers overnight. Suddenly, projects that used to take weeks are getting done in days. That's what's happening inside the Pro. And all that extra muscle translates into raw power. 16.7 teraflops compared to the PS5's 10.28. If teraflops sound like a made-up gamer currency, think of them like horsepower. The Pro basically strapped a turbocharger onto the PS5's engine. And here's the kicker. Sony managed this without moving to a smaller manufacturing process. They're still on the same 6 nanometer tech as the PS5 Slim. So instead of shrinking the kitchen, they train the chef to cook in 3 different cuisines at once. That's bold and risky. The real flex, though, is ray tracing. On the regular PS5, ray tracing is like extra seasoning. Nice when it works, but it slows everything down. On the Pro, Sony says ray tracing runs 2 to 3 times faster. Suddenly, puddles in games don't just look wet, they actually reflect neon signs in headlights. Shadows bend realistically instead of looking like fuzzy blobs. Glass looks like glass, not plastic wrap. And here's the crazy part. These ray tracing features don't even exist in PC GPUs yet. Let that sink in. If you built a $2,000 gaming rig today, it still wouldn't have some of the ray tracing tricks Sony baked into the Pro. That's wild. Usually consoles are the ones playing catch-up, but this time, Sony's leapfrogging ahead. Of course, stuffing future tech into today's silicon isn't simple. Every Pro GPU has to be tested way more brutally than regular PS5 chips. It's not just, does this thing run? It's, can it handle workloads from the future without melting down? If a chip can't cut it, it gets thrown into the reject bin. That means higher rejection rates, lower yields, and much higher costs per chip. Sony's basically running a silicon Hunger Games, and only the strongest survive. And those survivors, they're expensive. Now here's what makes this so fascinating. Sony didn't need to do this. They could have slapped a slightly larger GPU in there, called it a Pro, and gamers still would have lined up, but they didn't. They gambled. They stitched together a Franken GPU nobody else has, integrated unreleased tech, and made sure it still runs every single PS5 game you already own. That's nuts, because normally, backward compatibility is the first thing that breaks when you mix architectures. Sony somehow pulled it off. This GPU story alone explains a big chunk of why the PS5 Pro costs so much. We're not talking about a lazy refresh. We're talking about a console that's packing experimental features no PC has, with rejection rates high enough to make accountants cry. And yet, Sony still ships it at a mass market level. That's ambition. That's them saying, we're not just keeping up with PCs, in some ways we're ahead of them. But the GPU is only part of the story, because the next upgrade, the memory, is where things get sneaky. The Pro still has 16 gigabytes of GDDR6 memory, just like the regular PS5, but here's the twist, they cranked up the bandwidth by 28%, pushing it to 576 gigabytes per second. If that sounds meaningless, think of it like this. The regular PS5's memory is a 6-lane highway during rush hour. The Pro just expanded it to 8 lanes and gave everyone Ferraris. Traffic? Gone. Data just flies. And then Sony added an extra 2 gigs of DDR5 memory just for the operating system. Why does that matter? On the regular PS5, the OS and games have to share memory like annoying roommates fighting over fridge space. On the Pro, the OS gets its own little fridge, which means your games get the entire 16 gigs of high-speed GDDR6 to themselves. For developers, that's like suddenly having a private studio instead of a shared office. More headroom, fewer bottlenecks, smoother performance. Of course, premium memory isn't cheap. These chips cost about 60% more than standard ones, and every single module goes through brutal stress testing before it's allowed into a console. We're talking Navy SEAL training for silicon. If a chip fails under pressure, it doesn't make it into your Pro. That's another reason why the console costs more. You're not just paying for memory, you're paying for memory that survived boot camp. So to recap the first act of our story, Sony built a Franken GPU from 3 generations of AMD tech, doubled or tripled ray tracing speeds, added features that don't even exist in PC hardware, overclocked the memory, and gave the OS its own dedicated space. And all of this had to be validated, tested, and produced at scale with rejection rates through the roof. That's where your extra $200 is going. And we're just getting started because Sony's real secret weapon isn't the GPU or the memory. It's something else entirely. So if the GPU is the heart of the PS5 Pro and the memory is the bloodstream, then Sony's secret weapon is like the brain. It's called PSSR, PlayStation Spectral Super Resolution. Sounds fancy, right? But what it really means is this console can cheat in a good way. See, rendering games at native 4K with all the bells and whistles is insanely demanding. It's like asking your brain to write an exam, run a marathon, and play chess all at once. Something's gonna give. On PC, NVIDIA's solution is DLSS, AI upscaling that takes a lower resolution image and blows it up so it looks like 4K, but runs much smoother. Sony looked at that and said, "Cool idea, but what if we do it our way?" Instead of slapping extra AI cores on the chip, they made the GPU itself handle the job. That's like telling your chef, "Hey, you're also gonna DJ the party tonight." Crazy, but somehow it works. PSSR can handle 300 trillion operations per second for 8-bit machine learning. That's enough horsepower to take a 1440p frame, upscale it beautifully to 4K, and still lock the frame rate at 60. And Sony spent 4 years cooking this up. 4 years! That's like half a console generation, and the reason is obvious. You can't just throw AI into a console and hope it works. Latency has to be razor thin. If pressing jump feels delayed because the AI is still touching up your frame, gamers will riot. Sony had to fine-tune this thing to deliver sharp images and zero noticeable lag. And the best part? Developers don't have to bend over backwards to use it. It's baked into the console, which means future games can tap into PSSR without building an entire separate pipeline. For you, it just means sharper graphics and smoother gameplay without even noticing the trickery. Now, all of this, the Franken GPU, the overclocked memory, the AI upscaling brain, comes at a cost. Literally. Let's break it down. The GPU alone, around $180 to manufacture. That's 50% more than the regular PS5's chip. The high-speed memory, $65 instead of $45. Add the extra DDR5 modules, the 2TB SSD, and the fact that Sony still uses liquid metal cooling, but with a more refined process because the Pro runs hotter, and you're looking at $420 in raw parts for every single unit. Compare that to $280 for the standard PS5. And that's before you factor in the $500 million Sony invested into R&D over 3 years. $500 million just to invent this hybrid GPU, build PSSR from scratch, and make sure it doesn't melt in your living room. Cooling deserves its own shout-out here, because look, the PS5 Pro runs hotter than the regular PS5. More compute units, faster memory, AI workloads, that's a lot of heat. Sony stuck with liquid metal, but here's the thing, applying liquid metal to a chip isn't like buttering toast. Do it wrong and you fry the whole system. So they refined the process, tightened quality control, and made sure every single unit could handle the extra heat. That's why you don't see Pro Meltdown headlines yet. All that precision? Yeah, it costs money too. Now let's step back and put this into perspective. $700 sounds steep, but what if you tried to build a PC with equivalent performance? Spoiler, you're not getting away with less than $1,200. Between the GPU, the SSD, the premium memory, and the cooling solution, you'd be bleeding cash. And then you'd still have to deal with drivers, Windows updates, random crashes, and the joy of troubleshooting why your brand new game refuses to launch. With the Pro, you just plug it into your TV, hit the power button, and you're in. This is where Sony is flexing. They're saying, look, we can deliver high-end PC gaming in a box for half the price. And whether you buy it or not, that's impressive. But the real question isn't can it? It's should you? For most people, the regular PS5 is still more than enough. It runs every game, delivers great visuals, and costs less. If you're a casual gamer, if you play FIFA, Fortnite, Call of Duty, you don't need the Pro. But if you're the type who notices when shadows look fake, or reflections don't line up, or frame rates dip below 60, then yeah, the Pro is for you. It's not just about playing games, it's about appreciating the tech flex behind them. Think of it this way, the PS5 is like a great mid-range car. Smooth, reliable, gets you where you need to go. The Pro is the tuned-up version with racing parts under the hood, You don't need it, but man, when you drive it, you feel the difference. And let's not forget storage. Sony ships the Pro with a 2TB SSD because let's face it, modern games are storage hogs. One Call of Duty install and half your drive is gone. With 2 terabytes, you can finally have more than 3 games installed without playing Which Child Do I Delete Today? That's another quality of life upgrade that adds to the cost, but also to the experience. Now, let's talk rejection rates again, Wakitsimwe. Because this is something people don't always think about. Not every chip Sony makes actually survives the testing gauntlet. The Pro chips are held to stricter standards because they have to handle legacy PS5 games and next-gen ray tracing features. If a chip can't pull double duty, it gets tossed. That means Sony wastes more silicon, which means each working chip costs more. You're basically paying for the Every single pixel inside the Apple Vision Pro is the size of a red blood cell. Not a grain of sand, not a strand of hair, a red blood cell. And Apple somehow packed 23 million of them into 2 tiny panels, each no bigger than a postage stamp. That single fact right there is why this thing costs $3,500. And honestly, after you see what goes into building one, you might wonder why it doesn't cost more. Today, we're ripping open the most complex consumer device ever manufactured, step by step, layer by layer, to show you the insane 47-step process that turns raw aluminum, molten glass, and microscopic silicon into the Apple Vision Pro. Let's get into it. Section 1. The aluminum frame. It all starts with a bar of aluminum. Not just any aluminum, Apple uses a custom alloy, and the process begins with extrusion. That means heating the metal until it's soft enough to push through a custom-shaped die, like squeezing toothpaste through a nozzle. Except the nozzle costs hundreds of thousands of dollars, and the toothpaste comes out as 12-foot bars of precision-shaped aluminum. Those bars are then cut to length by an automated saw. Now, here's where it gets wild. That cut piece of aluminum gets loaded into a 3-axis CNC mill, where spinning cutting tools start hogging out the rough shape. We're talking about removing nearly 80 to 90% of the original metal, most of that aluminum recycled. But the frame that's left behind is a lightweight skeleton, designed to hold sensors and components with micron-level accuracy. After the initial rough cut, the part moves to a 5-axis CNC machine, one of the most expensive pieces of equipment in any machine shop. This thing doesn't just move left, right, up, and down. It can tilt, rotate, and carve freeform 3-dimensional surfaces that would be impossible on a standard mill. Apple uses this to sculpt the curves and contours of the Vision Pro's inner frame. Every pocket, every channel, every mounting point with tolerances tighter than a human hair. Then comes automated polishing. A robotic arm fitted with a melamine foam pad. Yes, the same stuff in a magic eraser buffs away every last machining mark. And if that's not enough, Apple hits the frame with laser ablation using focused laser beams to vaporize microscopic burrs and imperfections that no polishing pad could reach. After that, the aluminum goes through anodizing, an electrochemical bath that grows a protective oxide layer onto the metal surface, giving it that signature silver finish and scratch resistance. That's 8 steps just for the frame, and we're barely getting started. Section 2, the front glass. Now pay attention, because this part is genuinely insane. The front lens of the Vision Pro begins as a flat, precisely layered glass sheet. A CNC glass cutter, not your grandma's glass cutter, but a machine with live tooling that controls the blade orientation without even touching the surface first, slices it into shape. No lead-in marks, no burrs, just a perfect cut. That flat sheet then moves into a precision glass forming mold. The glass is heated past its softening point and pressed into shape under vacuum and heat, using a graphite mold that mirrors the final curved geometry of the front lens. This is the same caliber of process used to make $10,000 cinema lenses. The mold itself is modular, built with removable inserts so engineers can fine-tune positioning without scrapping the entire tool. Here's the brutal part. During this molding process, even one speck of dust will cause a visible optical distortion. one particle. If they spot it, they scrap the whole piece and start over. That's how tight the tolerances are. After forming, the glass goes through edge beveling on a 5-axis mill, then lens, edge blackening to prevent light leakage, and finally curing under heating elements. Every single piece is then run through automated optical inspection, where laser profilers and vision systems verify that the geometry is within spec down to the micron. That's 8 more steps. And we haven't even touched the displays yet. Section 3. The Micro OLED displays. This is where Apple spent the real money, and this is the component that makes or breaks the entire device. Each Vision Pro has 2 Micro OLED displays made by Sony. Each one measures just 1.25 inches, literally the size of a postage stamp, but packs enough pixels to exceed the resolution of a 4K television. Combined, that's 23 million pixels with a pixel pitch of just 7.5 microns. To put that in perspective, you could fit 54 Vision Pro pixels inside a single iPhone 15 Pro pixel. The pixel density hits around 3,400 pixels per inch. Nothing else on the consumer market comes close. But here's what most people don't realize. These displays aren't just slapped onto a circuit board. The backplane is silicon. Apple designed the silicon architecture, and Sony handles the OLED deposition, encapsulation, and driving circuitry on top of it. The manufacturing starts the same way computer chips are made, with the Czochralski process, where a seed crystal is dipped into molten silicon to grow a massive cylindrical ingot, which is then sliced into ultra-thin wafers, patterned and etched at the nanometer scale. Then the organic OLED materials are deposited on top in ultra-clean conditions. Because you can't deposit individual red, green, and blue subpixels at this scale in mass production, they create white light and pass it through color filters. That process alone eats 70 to 80% of the light output, which is why these displays need to pump out thousands of nits of brightness just to look normal to your eye. Sony produces these exclusively in Japanese fabrication facilities, and yield rates are a constant battle. Any defect at any layer means the entire display is toast. Apple reportedly pays $228 per display, meaning $456 just for the 2 screens. That alone is nearly a third of the total $1,542 bill of materials. Section 4. The optics. Between those displays and your eyes sits a 3-element pancake lens system, and this is where Apple's optical engineering borders on witchcraft. Pancake optics work by folding the light path, bouncing light between polarized surfaces and reflective layers to dramatically reduce the distance between the display and the lens. This is what keeps the Vision Pro from being the size of a shoebox. The key innovation is something called a quarter wave plate, or QWP. This component converts linear polarization to circular polarization, essential for the light folding trick to work. The problem? A quarter wave plate can't be bent or deformed, so Apple figured out a way to embed it between 2 cylindrical surfaces, allowing the QWP to remain flat while being cylindrically rolled inside the lens assembly. The first lens is literally split into 2 parts by this cylindrical cut. It's a solution so elegant that it's protected by Apple patents. Each lens element has intentionally uneven thickness, thicker on one side, thinner on the other, to optimize the field of view and eye relief distance. After assembly, every single optical unit goes through precision alignment using reflective markers and laser metrology to ensure perfect positioning relative to the displays. Section 5. The chips and sensors. Now let's talk brains, because this headset has 2 of them. The Vision Pro runs on 2 chips, the Apple M2 and the custom-designed R1. The M2, the same chip that powers the MacBook Air, handles the operating system, apps, computer vision algorithms, and graphics. It's manufactured by TSMC on a 5-nanometer process, packing an 8-core CPU, a 10-core GPU, and a 16-core neural engine with 16 gigabytes of unified memory. But the real star of this device is the R1 chip. This thing is purpose-built for one single job, processing data from every sensor on the device and streaming images to the displays within 12 milliseconds. That's 8 times faster than the blink of an eye. It pulls data simultaneously from 12 cameras, 5 sensors, and 6 microphones. Yes, and it does it with 256 gigabytes per second of memory bandwidth. Those 12 cameras include 2 high-resolution main cameras, 6 world-facing tracking cameras, 4 infrared eye tracking cameras inside the headset, plus a true-depth camera and a LiDAR scanner. The LiDAR uses direct time-of-flight technology. It shoots a 940 nanometer laser beam and measures how long the reflection takes to come back, mapping your entire room in 3 dimensions. Section 6. The EyeSight display, audio, and soft goods. Here's a feature that blew people's minds when Apple first announced it, and then frustrated them when they actually tried using it in real life. The EyeSight display is an outward-facing OLED screen on the front of the headset that shows a digital rendering of your eyes to people around you. The idea is to make the wearer seem less isolated. But here's the engineering behind it. Apple layered a lenticular lens on top of that OLED panel, the same technology used in those holographic postcards you had as a kid. The lenticular ridges display different images at different angles, creating a stereoscopic 3D effect of your face. Section 7. Final assembly and testing. Everything converges at Luxshare's factories in China. This Shenzhen-based manufacturer is the sole assembler of the Vision Pro, a company that earned Apple's trust by being willing to test what insiders call crazy ideas in prototyping and manufacturing. Luxshare beat out even Foxconn for this contract. During final assembly, micro-welding secures the aluminum frame components together. The custom micro OLED displays and 3-element lens system are placed with extreme care. Any misalignment at this stage ruins the entire optical calibration. The 12 cameras, LiDAR scanner, and all sensor arrays are mounted and connected. Then the external battery, a machined aluminum pack weighing about 12.5 ounces with a 35.9 watt-hour capacity. Section 8. The real cost. So here's the thing no one talks about. That $1,542 bill of materials? That only covers raw parts. It doesn't include the billions Apple spent on research and development over 7 years. It doesn't include assembly labor, packaging, shipping across the Pacific, import duties, warehousing, retail staffing, marketing campaigns, software development, or the ongoing engineering of Vision OS. When you factor all of that in, Apple's margins on this device are far thinner than people assume, especially when they're only shipping around 400,000 units a year. For context, Apple ships over 200 million iPhones annually. The Vision Pro isn't a cash cow, it's a statement piece. It's Apple proving that the future of spatial computing can be built today. What if luxury wasn't just worn, but forged under the heat of 1,000 degrees, behind locked doors, under intense secrecy? And what if the gold on your wrist didn't just look premium, but was made from scratch by the very people who engineered the watch itself? Welcome to the inner sanctum of Rolex, where gold doesn't just shine, it's built to endure. Inside the Rolex manufacturing facility, it's not just craftsmanship, it's total control. Every grain of gold, every molecule of steel, every flicker of lume, it's all Rolex. And they wouldn't have it any other way, because to Rolex, perfection isn't just a goal, it's standard procedure. Let's start right at the core of the operation. The Gold Foundry. Rolex is one of the very few luxury watchmakers in the world. Actually, scratch that, it's the only one that makes its own gold and platinum in-house. Not sourced, not subcontracted, not outsourced. Made. Right there, inside the Rolex compound in Geneva. Now picture this, 24-karat pure gold bars, gleaming and heavy, arriving at the Rolex facility. But Rolex doesn't just slap that gold into a case or bracelet. That would be too easy. And way too soft. See, pure 24-karat gold is beautiful, but it's also far too malleable for everyday wear. It scratches, it dents, it bends. Not exactly the kind of material you'd want on a timepiece that's built to last generations. So what does Rolex do? It melts the 24-karat gold, heats it until it's a glowing liquid, then uses specially guarded recipes to blend it with exact proportions of other metals: silver, copper, platinum, palladium. Each of these alloys is added in meticulous ratios to create Rolex's iconic 18-karat golds: yellow gold, white gold, and their legendary Evrose gold, Rolex's own patented take on rose gold. But here's the thing, it's not just about color, it's about structure. Rolex engineers these blends so precisely that the resulting metal isn't just beautiful, it's engineered for resilience. Every pore is measured, timed, and controlled. The temperatures are tightly regulated, the humidity, even the ambient air quality in the foundry matters. The alloying process isn't some off-the-shelf operation. It's a ritual, done by trained hands, guided by proprietary data, conducted in an environment that Rolex has optimized down to the last cubic meter. The workers operating these furnaces are more than technicians. They're metallurgical artists. Once the metals are added, the mixture is stirred in exact cycles. It's not about speed, it's about consistency. One wrong ratio, 1 second too long, and the entire batch could be off. Rolex isn't just chasing a gold standard, it defines the gold standard. After alloying, samples are pulled from the molten blend and tested immediately. Right there in the foundry, on-site spectrometers analyze the mix at an atomic level. If the sample doesn't meet Rolex's standard, it's rejected on the spot. No close enough, no maybe later, just out. The accepted alloy is then cast into molds to form long rods or bars, which will later be processed into sheets, links, cases, or bezels. But even this casting phase is custom to Rolex. The molds are specially designed to reduce porosity, eliminate microcracks, and ensure even cooling. After solidification, those gold bars are set aside to rest. Yes, rest. Rolex lets the metal stabilize. It's a step that sounds simple, but is critical. As the metal cools, stress is relieved from the structure. It's like letting bread dough rise, except instead of yeast, it's metallurgy. Then begins the transformation from raw gold bar to usable component. The bars are milled down, cut into blanks, and inspected again. Edges are checked for uniformity, surfaces are checked for density, grain direction is monitored. Rolex isn't leaving anything to chance, and when it's finally time to shape the components, that's where the human touch returns in full force. Craftsmen and women take those gold blanks and start forming bezels, cases, and links. Each piece is cold-formed under pressure to maintain metal strength. The forming tools used are Rolex-designed, custom-built, serviced constantly. Some are even made with diamond-coated elements to maintain edge accuracy. Because gold is soft, but Rolex gold isn't allowed to behave that way. The components are then heat-treated again, going through annealing ovens to bring them to the perfect molecular tension. Not too hard, not too soft. The result? A piece of 18-karat gold that wears like steel, but glows like treasure. And throughout all of this, every batch, every pore, every component is tracked. Rolex logs every stage of transformation for internal consistency. The metallurgy is archived. The performance of each alloy batch is recorded. It's like a lab notebook for luxury. This is how Rolex guarantees that their gold doesn't just shine today, it shines the same 10 years from now, 20 years, 50. The color, the durability, the resistance, it all holds because it was engineered to, not guessed, not hoped, engineered. This entire approach from molten gold to machined case exists so Rolex can say something no one else can. This gold is ours. Every atom, every shade, every edge, controlled, created, and perfected within the walls of one company. This process happens inside a purpose-built foundry Rolex introduced in the early 2000s, and it's not open for tours, not even for industry insiders. No photos, no video. Rolex guards this operation like a Swiss vault, But through carefully controlled disclosures and insider accounts, we now know what happens inside. It's the kind of place that feels more like a high-security research lab than a workshop. Swipe card access, retinal scanners, only essential personnel are allowed beyond certain doors, and everyone who enters is bound by strict confidentiality agreements. Even suppliers who deliver raw materials rarely get to see where that material ends up. Rolex compartmentalizes every aspect of the process. Need-to-know basis. Always. The fewer eyes, the fewer leaks. That's how secrets stay secrets. There are no press visits, no influencer walkthroughs, no behind-the-scenes documentaries. Not even close. The Foundry is a black box, and Rolex intends to keep it that way. The only reason we know anything at all is because Rolex allows just enough information to slip through. Just enough to confirm it exists, but not enough to replicate. The culture inside is monastic, focused, quiet. There are no loud machines whirring constantly. The equipment is advanced, but the environment is surprisingly calm. Rolex believes precision thrives in stillness. Tools aren't left out. Everything is cataloged, cleaned, stored. The place runs like a Swiss watch, pun fully intended. Even small tasks like transferring metal samples are done with a kind of ritualistic care that borders on obsessive. Visitors, when they are granted access to the building's outer areas, are watched closely. You won't find anyone wandering off or pulling out a smartphone. It's not even allowed inside most sections. The entire perimeter is controlled, cameras, sensors, and layers of security. And Rolex doesn't just keep this process locked down for show. It's because the techniques used inside the Foundry, the recipes, the casting methods, the finishing techniques, are 100% proprietary. Competitors have tried to reverse engineer Rolex alloys for decades. They've gotten close, but never quite there. Because without knowing the exact processes used, the atmospheric conditions, the resting periods, the microscopic tests, the results are always just a little off. Rolex knows this. That's why they don't outsource. That's why they don't brag. They just work, quietly, meticulously, behind those thick Geneva walls. Even the Foundry's physical location within Rolex facilities isn't promoted. There's no big sign, no separate entrance. From the outside, you'd never know it was there. Just another anonymous-looking building in a quiet industrial zone. But inside, that's where the transformation happens, where raw gold turns into Everose, where alloys are born, where case blanks take shape, where the materials that define Rolex's legacy are literally forged. This is where Rolex's magic is made, not in marketing decks or fancy boutiques, but in fire, pressure, and secrecy. The Foundry is the heart of the brand, and it beats behind locked doors. Foundry men melt 24-karat gold over roaring flames. That molten gold is then poured through a sieve, creating droplets that fall into vats of water. The instant cooling hardens them into beads of 18-karat gold. Those beads are the starting point for Rolex's cases, bezels, crowns, and bracelets, and that's only step one. And the same extreme level of control applies to Rolex's other materials. Take oyster steel, for example. This isn't just any steel. It's a 904L stainless steel, an ultra-resistant high-performance alloy that Rolex has used since the mid-80s. 904L steel isn't easy to work with. It's tougher, more durable, and more resistant to corrosion than the more common 316L used by most other watchmakers. But Rolex wasn't interested in what's easy. They were after what's better. 904L, or as they call it, oyster steel, offers unmatched brilliance when polished. That mirror-like shine? It doesn't come cheap. Before Rolex even begins shaping it, this steel is examined under microscopes. Every grain, every layer. If the microstructure isn't right, it doesn't make the cut. Once approved, the metal is primed, hardened, and refined again. Then finally, expert polishers unlock that signature glow that sets Rolex apart. And then there's Rolsor, another Rolex original. It's a marriage between oyster steel and gold. Toughness meets elegance. Rolsor combines the core strength of steel with the nobility of 18-karat gold, usually seen in the bezel, crown, or center links of the bracelet. It's become a visual signature, that seamless blend of luxury and durability. And speaking of innovation, what Rolex does with light is equally impressive. Enter ChromaLight. Back in 2008, Rolex unveiled this breakthrough display tech. During the day, the markers look crisp and clean, but at night, the glow is unmistakable, a deep, piercing blue, not the green lume you see on most other watches. ChromaLight is more than just good looks. It's engineered to store ambient light energy, then release it slowly and evenly in dark conditions. It's a custom-developed substance made from a blend of aluminum, strontium, dysprosium, and europium, which is first powdered, then heated, then blended with resin, and applied by hand to each dial marker and hand. This level of precision is what defines Rolex. From metals to lume is either developed, refined, or crafted entirely in-house. They don't chase trends, they engineer timelessness. Take RLX titanium, for instance. Rolex could have easily adopted standard titanium years ago. Lots of brands did. It's light, strong, corrosion-resistant, but Rolex wanted more control. RLX titanium is a special grade 5 titanium alloy, and Rolex spent years studying its properties before deciding to bring it in-house. Now, think about all these materials. Gold, steel, titanium, platinum, and imagine the coordination it takes to blend them into a single cohesive timepiece. That's why Rolex doesn't outsource its research and development. They have full-scale professional labs on site, chemistry labs, physics labs, stress testing chambers. Watch components get tested under brutal conditions, extreme heat, cold, moisture, shock. Each part gets tortured before it ever ends up on a customer's wrist. If it breaks, it goes back to the drawing board. If it survives, it earns the crown. This obsessive attention to material science is why a Rolex feels different, why it lasts, why it means something. It's not just the logo, it's the years of metallurgy, testing, and hands-on craftsmanship behind every element, even the ones you never see. No shortcuts, no compromises. Rolex controls everything, and this control means that when a $50,000 Daytona or Day-Date rolls off the line, it's not just a luxury object. It's a material marvel, forged from raw elements reshaped by science and perfected by hand. So next time someone says it's just a watch, show them the Rolex Foundry. Show them the steel that's scanned on a microscopic level. Show them the rose gold that never fades. The glow-in-the-dark markers built from rare earth elements, the titanium that shimmers like silver even after years of wear. Because a Rolex isn't just built to look good, it's built to outlast, built to perform, built to live. And when you wear one, whether it's a classic Datejust or a cutting-edge Yachtmaster, you're not just wearing gold or steel. You're wearing decades of research, an obsession with detail, and a relentless pursuit of mastery, all forged from a single bar of gold. If you found this deep dive into the Rolex Gold Factory as fascinating as we did, make sure to like, subscribe, and hit that bell icon so you don't miss out on more behind-the-scenes stories of craftsmanship, luxury, and innovation.